Have you ever stood in the heart of a city at night, looked up, and felt truly alone? All around you, a galaxy of artificial light, a testament to human power, burns against the darkness. We have conquered the night, bathing our world in a constant, electric day. We light our streets, our monuments, our homes, and our offices, sending trillions of photons of energy beaming onto sidewalks, glass windows, and stone facades. And we assume all that light, all that energy is wasted, that it hits the cold, sterile concrete and simply ends. We see these surfaces as deserts, lifeless, and inert. What if we are wrong? What if all that wasted light, all that energy we pour into the void, isn't being wasted at all? What if, in the shadows of our illuminated world, something is listening to that light? What if something is eating it? This is the story of an ecosystem we built by accident, a wilderness hiding in plain sight. We are surrounded by a new form of nature, one that is evolving not in a primordial soup, but on the glass and steel of our skyscrapers. Our cities, which we believe to be the very antithesis of nature, may be the planet's newest biological frontier. To see it, you just have to change the way you look at grime. This isn't a story about the future, about some distant, speculative life. This is happening right now on a global scale. The facts are staggering. More than 80% of the world's population, and a staggering 99% in Europe and North America, lives under skies polluted by artificial light. This constant illumination is known as ALAN, or artificial light at night. For decades, we have studied its negative effects. How it disrupts our sleep, how it confuses migrating birds and sea turtles. But we have almost entirely missed the other side of the story. We have focused on the absence of darkness, but we have failed to properly investigate the presence of a new, permanent energy source. For billions of years, life on Earth has been bound to a single, fiery clock. The sun. A cycle of feast and famine. Light, then dark. Energy, then scarcity. We, in our infinite and accidental ingenuity, have broken that cycle. In our cities, the sun never truly sets. And where there is a constant, reliable source of energy, life, in its relentless opportunism, will always find a way. The surfaces of our modern world, the concrete of a bridge, the marble of a statue, the glass of an office tower, we see them as sterile. We clean them, we pressure wash them, we scrub them free of the green and black stains that inevitably appear. We call it grime, pollution, dirt. But it is not just dirt. It is a living, breathing community. A thin, green, slimy layer that is, in reality, a teeming, microscopic jungle. And the glow of our streetlights is its sun. Every living thing you've ever seen, from the smallest ant to the largest whale, is in a constant, desperate search for three things. Three simple pillars that support the entire edifice of biology. A source of water, a source of food, and a source of energy. Fail to find any one of them and you are gone. For most of history, the surfaces of a dry rock or a sheer pane of glass have been biological deserts precisely because they failed to provide one or more of these three ingredients. A bare rock in the sun is too hot, too dry. A glass window is inert. Life gets no foothold. But in the city, we have accidentally, painstakingly, created the perfect conditions. We have built an oasis for an organism we never knew existed. Let's start with water. A city surface seems dry. But think about the urban environment. Cities create their own microclimates. They are urban heat islands, often several degrees warmer than the surrounding countryside. This temperature differential, combined with the humidity from rivers, parks, and millions of breathing humans, creates a world of condensation. When the sun goes down, the hard, non-porous surfaces of stone and glass cool faster than the air. Water materializes from the atmosphere, sweating onto these surfaces. Add to this the humidity trapped in the urban canyons between tall buildings, the fine mist from traffic on wet roads, and, of course, regular old rain that splashes and clings. The city is, to a microorganism, a surprisingly damp place. Water is not a constant flood, but it is a reliable, recurring film. Pillar 1, solved. Next, nutrients. What could possibly be food on a pane of glass? The answer isn't on the glass, it's in the air. Our air is thick with a soup of suspended particles. We call it dust, but it's so much more. It's a fine dining menu for a microbe. It contains mineral dust from construction sites, salts, pollen from parks, and microscopic fragments of tire rubber and asphalt. But the real delicacy, the true fertilizer, comes from our single greatest sin of pollution, our exhaust. The tailpipes of our cars and the smokestacks of our industry pump millions of tons of nitrogen oxides and sulfates into the atmosphere. These compounds dissolve in the water droplets in clouds and rain, becoming nitrates and sulfates. In human terms, we call this acid rain. In biological terms, we call it fertilizer. This is the exact same food that farmers put on their fields. We are, quite literally, fertilizing the sides of our buildings every single day. Pillar 2 solved. And that leaves the final, most important pillar, energy. This has always been the single limiting factor. On a bare rock, a microbe could get water from the rain and nutrients from the air, but it only had energy for 12 hours a day at best. And that solar energy is brutal. The full blast of the sun comes with desiccating heat and sterilizing ultraviolet radiation. It's a hard life. And then we flipped a switch. We invented the light bulb, the neon sign, the high-pressure sodium lamp, and the LED. Suddenly, there was a new energy source. A cold sun. It wasn't brutally hot. It had no UV radiation. And, crucially, it never set. For a creature that feeds on light, this was the sound of a dinner bell that never stops ringing. The 12-hour famine was over. The feast could be permanent. The light that streams from a street lamp, the upward-facing floodlight on a monument, the all-night glow of a billboard. This isn't just illumination. It's a free, 24/7 buffet. Pillar 3 solved. The niche is complete. Water, nutrients, and a constant, gentle, reliable source of energy. We have built it, and they have come. So, if there's a feast laid out on our city walls, a niche that has never before existed in Earth's history, who exactly is coming to dinner? When you see that green, slick film on a stone statue, or that dark, sooty stain on a glass window, you might think it's moss, or perhaps the beginning of lichen. But it's neither. What you are looking at is something far more ancient, far more adaptable, and far more important. You are looking at the pioneers. You are looking at a phototrophic biofilm. Biofilm is a word that sounds technical, but you already know exactly what it is. It's the slime on a river rock that makes it slippery. It's the plaque that your dentist scrapes from your teeth. A biofilm is not a single organism, but a complex, crowded city of microorganisms. These microbes band together and secrete a sticky, slimy matrix, a fortress of sugars and proteins that holds them together, protects them from harm, and traps water and nutrients. It is a collective, a cooperative, a microscopic metropolis. And the phototrophic part? That simply means they feed on light. These are the primary producers, the plants of this new urban jungle. But they are not plants. They are, in many cases, the organisms that invented the very concept of feeding on light. Meet the main architect of this new world, cyanobacteria. You may know them by their old, misleading name, blue-green algae. But they are not algae. They are bacteria. And they are, without exaggeration, the most important organisms in the history of this planet. They are ancient. The oldest fossils of cyanobacteria date back 3.5 billion years. For comparison, the first land plants are a mere 450 million years old. These are the beings who, in the planet's infancy, invented the trick of photosynthesis. And in doing so, they began to release a toxic waste product, oxygen. Over 2 billion years, they slowly, relentlessly pumped this gas into the atmosphere, triggering the Great Oxidation Event, killing off most other life on Earth and paving the way for, well, for us. Every breath you've ever taken, you owe to them. And here is the crucial part. They are tough. They are extremophiles, the masters of survival. They've been found in the boiling hot springs of Yellowstone, in the hypersaline lakes of the Andes, and frozen solid in the Antarctic ice. They are the absolute masters of colonizing bare, lifeless surfaces. A rock, a desert, a volcanic crater, that's their natural habitat. So, a nice, temperature-controlled, constantly watered, fertilized, and illuminated stone facade in Paris, London, or New York. That's not a challenge. That's a vacation. They are not alone. They are often joined by partners like diatoms. Diatoms are a type of single-celled algae, true eukaryotes like plants and animals. They are famous for building intricate, beautiful shells around themselves made of silica, pure glass. They are the jewels of the microscopic world. They, too, are photosynthetic, and they, too, are astonishingly adaptable, thriving in any body of water, including the thin, temporary films of water on a building. Together, the cyanobacteria, the diatoms, and a handful of other green microalgae form this pioneer community. They are the base layer. They are the foundation of this brand new food web. They are the ones who have figured out how to do the impossible. How to eat a streetlight. Here's where the story gets truly strange. You might think, light is light. But to a photosynthetic organism, this is like saying food is food. To us, the difference between a steak and a donut is obvious. To a microbe, the difference between sunlight and a streetlight is just as profound. In fact, it's the difference between a fully stocked organic buffet and a vending machine that only sells orange-colored candy bars. To understand this, we have to talk about color. What we see as white sunlight is actually a perfect, smooth rainbow of every color, from deep reds, through the greens and yellows, to the blues and violets. This is a full spectrum. The pigment that plants on Earth have evolved to use, chlorophyll, is a picky eater. It loves to absorb energy from the red and blue parts of that spectrum. It hates the green part. It reflects green light away, which is, of course, the single reason why the entire plant-covered world is green. Now, look at our artificial lights. They are not full spectrum. They are junk food. They are incredibly spiky. The old high-pressure sodium lamps, the ones that cast that familiar, eerie, orange-yellow glow over cities for decades, are a perfect example. Their light spectrum is almost entirely one massive spike in the yellow-orange part of the spectrum. For a plant's chlorophyll, this is a disaster. It's the color of light it has no interest in eating. A forest of plants trying to live under a sodium lamp would starve to death. And what about our new, efficient lights? The bright, white LEDs that are rapidly replacing them. They're also spiky. Their spectrum is typically a huge spike of energy in the high-energy blue part of the spectrum, with a secondary, broader hump in the yellow-green, and almost nothing in the red. Again, it's a bizarre, unnatural diet. So here is the central mystery. If our artificial lights are junk food that normal plants can't eat, why are our buildings turning green? The answer lies in the ancient, alien-like biology of the cyanobacteria. They are not normal plants, and chlorophyll is not their only weapon. Over billions of years, competing in the deep, dark oceans where light is filtered and strange, they evolved a secret weapon. They developed a set of accessory pigments. These are other molecules in their cells that act like satellite dishes, designed to catch the channels of light that chlorophyll misses. And they have names as beautiful as their function. There is phycocyanin, a stunning blue pigment, and phycoerythrin, a vibrant red one. Now look at the junk food light again. That massive, useless orange spike from the sodium lamp? It just so happens that the blue pigment, phycocyanin, is perfectly tuned to absorb that exact color of light. It's a match made in heaven. The waste light that chlorophyll ignores is a gourmet meal for phycocyanin. And what about the new LEDs with their massive blue spike? The red pigment, phycoerythrin, and even phycocyanin itself are brilliant at absorbing light in the blue-green-yellow parts of the spectrum. This is the mind-blowing part. These pigments, which evolved billions of years ago, perhaps to catch the dim, blue-green light filtered down to the bottom of the ocean, or to live underneath other organisms, have accidentally perfectly pre-adapted these microbes for our most modern technology. They are not just surviving on our artificial light. They are thriving. They are uniquely and perhaps better suited to eat the light from an LED than they are to eat the light from the sun. We thought we were building sterile cities of metal and glass. Turns out we were building the perfect 24/7 all-you-can-eat buffets for the most ancient and adaptable life on Earth. A thin layer of slime on a building. So what? Why should we care if an ancient bacterium, a rock-eater, gets a free meal from a street lamp? It might seem like a simple scientific curiosity, a weird nature fact. But the impact of this new ecosystem is far-reaching, expensive, and is unfolding right under our noses. This is not a passive relationship. This grime is not just sitting there. It is active, and it is hungry. First, let's talk about biodeterioration. That's the scientific term for what's happening to our cultural heritage. The biofilm, that city of microbes, isn't just feeding on light. It needs minerals to build its city and its own cellular machinery. And where does it get those minerals? From the surface it's living on. The cyanobacteria and their partners are not polite tenants. As a byproduct of their metabolism, their simple act of living, they secrete a cocktail of chemicals including mild organic acids. These acids are a powerful solvent. If the surface is stone, marble, limestone, or sandstone, these acids begin to dissolve the mineral glue holding the stone together. It's a slow, relentless chemical assault. But it gets worse. That slimy matrix, the fortress the biofilm builds, its primary purpose is to hold on to water. It acts like a microscopic sponge, trapping humidity and rainwater directly against the surface, preventing it from evaporating. This means the stone or concrete never truly dries. In winter, this trapped water freezes, expands as ice, and creates microfractures. The freeze-thaw cycle, repeated night after night, acts like a tiny chisel, flaking, spalling, and cracking the surface apart. This is not a theoretical threat. This is the single greatest threat to our physical cultural history. The magnificent cathedrals of Europe, the ancient marble statues of Rome, the intricate carvings on historic government buildings, even modern 20th century concrete landmarks. They are being, in the most literal sense, eaten alive. We spend hundreds of millions of dollars every year pressure washing, scaffolding, and restoring these structures. We are in a constant war with this grime, but we are losing because we've been fighting the symptom, not the cause. The cause is the food source we provide, free of charge, every single night. But the consequences don't stop at our buildings. They create a new beginning. Where there are primary producers, consumers will always follow. It is the ironclad rule of ecology. You cannot have a meadow without a grazer. And so, this urban jungle has its own animals. If you were to take a sample of that biofilm from a statue and put it under a microscope, you would enter a new world. You would see the grazers of this new ecosystem. You would see tiny, 8-legged mites, arachnids crawling through the slime. You would see microscopic rotifers, animals, with crowns of cilia spinning like turbines, pulling in water and cyanobacteria. And, if you are lucky, you will find the most charismatic and indestructible creature on the planet. Tardigrades, the water bears. These microscopic, 8-legged, vacuum of space surviving, radiation-proof superstars are here. They are crawling on the side of a glass skyscraper in downtown Tokyo, navigating the film of water, and grazing on the fields of cyanobacteria illuminated by a nearby billboard. This is a food web, an ecosystem in its entirety. It starts with our waste light. That light feeds the cyanobacteria. The cyanobacteria are eaten by the rotifers and tardigrades, and those, in turn, are eaten by other microscopic predators. It is an entirely new, entirely artificial synthetic food web built on a foundation of human technology. A new nature, born from our electric light. We are in the middle of a global experiment, and we're not even watching the results. In fact, we're actively and accidentally accelerating it. Right now, almost every city on Earth is in the process of a massive technological shift. The great switch from the old orange-yellow sodium lamps to new, hyper-efficient, bright white LEDs. We are doing it for the right reasons, to save energy, to reduce our carbon footprint, and to save money. It seems like a win-win. But we've forgotten about the organisms we're feeding. Remember the light diets? The old sodium lamps were like a vending machine with one kind of candy bar. The cyanobacteria, with their phycocyanin pigment, could eat it, but it was a limited menu. The new LEDs, with their powerful blue spike and broad green-yellow hump, are not a better vending machine. They are a gourmet buffet. That blue spike, in particular, is a high-energy, all-you-can-eat feast for the accessory pigments. In our quest for efficiency, we have unintentionally switched from a junk food diet to a superfood diet for these biofilms. We are upgrading their meals. It is entirely likely, and studies are beginning to show it, that the spread of LEDs is accelerating the growth of these phototrophic communities. We are speeding up the biodeterioration of our own infrastructure. The grime is growing faster, the damage is happening more quickly, and our cultural heritage is paying the price for our efficient light. This leaves us standing at a crossroads. We are faced with a fundamental choice, and two very different paths stretch out before us. The first path is the path of war, the path we are currently on. This is the path of control. If we now understand how they are feeding, perhaps we can be smarter in how we fight them. If we know the exact wavelengths of light the pigments absorb, could we design an inedible light? Imagine a smart LED for a city, a light that is tuned. It would have all the colors we need to see clearly and perceive white light, but it would have precise surgical valleys, gaps in the spectrum, right where the phycocyanin and phycoerythrin pigments have their absorption peaks. We could, in theory, create a light that is bright to our eyes, but dark to a cyanobacterium. This is a monumental engineering challenge, but it is no longer science fiction. It is a necessary next step in urban design. But there is a second path, a more radical, more ecological path, the path of harmony. If you can't beat them, join them. What if this isn't a problem, but an opportunity? We have identified an organism that eats light and eats our air pollution, the nitrogen oxide fertilizer, and thrives on our vertical, sterile surfaces. What if, instead of fighting it, we domesticated it? Imagine living walls or biofacades that are not just decorative planters, but functional, living skins for our buildings. We could design panels that encourage the growth of a specific, non-damaging species of cyanobacteria. We could seed our buildings. At night, the waste light from our streets and offices would power this biofilm, and in return, this living skin would do a job for us. It would scrub the air, metabolizing the nitrogen oxides and other pollutants, literally breathing our city clean. It would provide an extra layer of insulation, cooling the building in the summer and warming it in the winter. It would be a self-repairing, carbon-capturing, pollution-eating layer, all powered by light we were already wasting. This is the great challenge of the Anthropocene, the age of humans. We have spent centuries trying to push nature out of our cities, to build sterile, controlled environments. But life is too stubborn. It adapts, it evolves, and it is finding its way back in, through the cracks on the glass, and in the light. Evolution didn't stop. It's happening right now on a statue near you on a timescale we can finally observe. The question is no longer if life will find a way. The question is whether we will be smart enough to see it, to understand it, and to decide if we want to be its enemy or its architect. Our cities are no longer just home to us. Our waste has become their world.